Hello students, welcome to Inside Physics. I am Srinivas. Today we are going to discuss about the psi function, which is a familiar function in quantum mechanics. As per quantum mechanics and de Broglie hypothesis, every moving particle or object is associated with a matter wave. Okay. So in this regard, the wave function has a significance, and this wave function tells something about that matter waves. Okay. In general, we know that light waves, sound waves, and water waves. These waves we already studied about, and they have some variation things in their propagation with respect to position and time. The variables, if you take in light waves, they are electric field and magnetic field, which vary with position and time. And in the same way, the pressure variations we can observe in sound waves. So if we take the same thing regarding the matter waves proposed by de Broglie, there is not a thing which can be similarly observed like we do in the light waves and sound waves. We cannot tell something about which are the variables in matter waves, but we can observe the matter waves by considering the wave function. We can study the matter waves by considering the wave function, and it is denoted by psi. This wave function is a complex valued function and it has no physical significance because this wave function is an observable quantity. Okay, so by that means what we can say is observable quantity means that this wave function will not exactly tell the position of the particle, but it can be considered as an index of the position of the particle in three-dimensional space, where we are going to find the particle. We want to find the position of the particle. But when we say we are trying to find the position of the particle, according to Heisenberg's uncertainty principle, there is an uncertainty. That means there is no certainty that exactly the particle is here. So that uncertainty, that means the probability of finding a particle in a particular space. If we say the term probability, if there is a chance, a surety is there, we can find the particle, then the probability we can say is equal to 1. Okay, these are the general terms regarding wave function, and we further move to the properties of wave function, and we will study what is a well behaved wave function. Okay, now we will see the probability interpretation of wave function. As I told you, probability of finding a particle in a small space where we consider that is equal to 1, and the same was proposed by Max Born, scientist name, in 1926. According to him, Max Born, according to him, the probability is can be written as the magnitude of the psi function, and is represented by the square of the magnitude of the psi. So he said that this value gives the probability of the particle finding its position in a particular space. Okay. So if the probability of finding a particle in a space which is has unlimited boundaries like minus infinity to infinity. Okay. So now here, see, the probability is proportional to, we can write the probability is proportional to psi of x y z whole square dv. dv is a small space where we can find the particle which we consider a small space, and x y z are the coordinates of the function psi. Psi is a function which is dependent on the position and time. See, in next condition we will also include the time aspect in this psi function. For now we can say, as per Max Born, probability is proportional to, see, the square of the magnitude of the function psi. So regarding the small space considered as dv. Okay, so here if you observe, this is magnitude is always a real value. Even though psi as a function is a complex valued function, the probability, that means the magnitude, square of the magnitude, will give a real value. Okay, here see, now I said the probability of finding the particle is in between minus infinity to infinity. That means, see, the particle, suppose we consider a microparticle, all the microparticles or atomic particles are associated with matter waves as per de Broglie hypothesis, as they are in continuous motion. So, if there is a chance of finding a particle in the entire space, the probability is definitely 1, because it is a surety that we will find the particle. But the space we are considering is minus infinity to infinity, it is an unlimited area. So, as we consider the psi function as a probability, and we are taking the limits from minus infinity to infinity, this can be written as minus infinity to infinity psi of xyz. It is a three-dimensional space. Xyz means dv is a space, three-dimensional space we are considering. We can write this as dx dy dz. Okay, so I said that psi is a complex valued function, right? We are discussing the general properties and the probability interpretation of the wave function psi. Okay, here if you observe, this gives the probability of finding a particle in the limits minus infinity to infinity for the position coordinate x y z, and these position coordinates gives a small space when you consider in dx dy dz, and it is termed as dv. Okay, so this complex valued function, see, the probability, so the multiplied by this square gives a real value function. So if you consider psi as a complex valued function, to get a real value we must multiply this with a complex conjugate. So psi star is denoted by complex conjugate. So this function can be written as a complex okay, see, this is the complex function, this is the conjugate of this complex function. So these are the probability interpretations of psi function given by Max Born. So now we see what is the normalization condition of psi function. When we say normalization, that means it interprets that the probability of finding a particle in the entire space is equal to 1. So see, here if we can write psi n of x, y, z, comma t, okay, is equal to c psi of x, y, z. Here we have included the coordinate time also, space coordinates x y z and t. See, Then see here, if this psi n is normalized wave function, psi n represents the probability density. Psi n represents the probability density. So here psi represents probability amplitude. Probability amplitude. See, probability and probability density. See, both are almost signifies the same thing. Okay. So here the normalization. Here, if you apply the limits again to this one, it will change to the limits minus infinity to infinity psi n of x, y, z, comma t gives this. This is called C is normalization constant. Okay. So here also we apply the limits minus infinity to infinity. Okay. So if you see here, if you observe, this is the normalization wave function. This is the normal wave function, and this is c square. This c is called normalization constant. Normalization constant. As we have discussed, this normalization condition is equal to 1. So here we can write the normalization constant as 1 by minus infinity to infinity psi of x, y, z, comma t. Okay, so here we can take the space dx, dy, dz. Okay, so this is the normalization of wave function, which gives a probability interpretation, and the normalization condition is that the probability of finding a particle in a space considered small volume is equal to 1. And so here we can say from the Max Born interpretation that if you observe this one, P is equal to okay. So this is the probability interpretation of wave function. Next, we will see what is a well-behaved wave function is about. Well-behaved means a wave function has to be a proper wave function, then it has to met with some criteria. So the first one is the wave function psi must be finite. Must be finite. Okay. See, what is a finite? See, if even though we consider the limits of finding a particle as infinite, that means x tends to minus infinity or infinity to minus infinity, y tends to infinity or to minus infinity, similarly z tends to infinity or minus infinity. So even though the coordinates are extending to the unlimited space, either minus infinity to plus infinity, psi value must be finite, because psi is always signifying the probability. As the probability is a finite value, that means finding all the sum of all the probabilities in all the three directions is equal to 1, then in this regard psi value must be finite, otherwise it has no significance as a interpretation of the probability of finding the particle. As already we have discussed, psi has no physical significance, it is only a observable quantity. So the next one, psi must be single valued. Psi must be single valued. That means, see, if at any point, a particular point or a particular position, if it has two real values, that means, see, the probability of finding the particle at that particular point has two values, which is absurd. So it has practically not possible. That means always psi must have a single valued at a particular position and particular time. So we are all talking about not exact position of the particle. Always we talk about the probability only, because Heisenberg uncertainty principle says that the probability of finding a particle has always an uncertainty in it. Okay. So psi must be a single valued function. Next one. The third one, here it is the second criteria that it should be met with to consider psi as a well behaved function. The third one, psi must be continuous everywhere. Psi must be continuous everywhere. So continuous means we know that we will consider the boundaries d by dx, d by dy, d by dz. So we are in three-dimensional space. So if it is met with any boundary, that means with varying potential. So at the boundary, even the potential is varying, the probability of finding the particle will be same, and the psi will not be a discontinuous function at the boundaries. That means, to understand it in a better way, see, if we have a boundary with some space inside and we are considering a particle, finding a particle with some probability inside this space, even we consider the point anywhere around the boundaries or inside, okay, see, anywhere in this space the psi must be continuous. It should not be a continuous. What happens if it is a discontinuous function at this point, suppose at this boundary? So here the probability will be having a zero value. So here the significance, see, the significance of psi function will be coming to an impractical value. So here in this way we will say the psi must be continuous everywhere, even inside the space and or even at the boundaries where the potential of the particle will be changing. So because the particle will be continuously moving, and at the boundaries the potential may change because it will be coming and moving to every position. So in this way we can understand what is the psi function, wave function, which is represented by psi, and we know the importance of matter waves in quantum mechanics. So this understanding of wave function will be very useful in further proceedings for the quantum mechanics. Okay, thank you.